everyone. Today we're presenting on efficient planarity testing using the Hopcroft-Tarjan algorithm, a linear time solution to one of the graph's theory fundamental problems. So let me just quickly introduce our team. My name is Parvis. I'm covering problem definition solution concept. Luis will explain the rest of algorithms phases, and Kim will wrap up with experimental results and conclusions. And yes, we're very camera shy, so we don't have images of ourselves, but you can still see us. Think of us as the hidden vertices of this presentation. So what is the problem? A graph is a planar if it can be drawn on a flat surface without edge crossings. So our goal is to determine whether a given graph is a planar, and crucially, we need to do it in a linear time big O of v. So when the answer is yes, we produce a valid planar embedding. When it's no, we return a Kuratowski certificate, either a K5 or a K3 and 3, subgraph proving nonplanarity. So why should we care about the efficient planarity testing? 3 reasons. First, circuit design. In VLSI manufacturing, physical wires on a printed circuit board cannot cross. A crossing would short circuit the board. So before fabrication, engineers must verify planarity. Second is a network visualization, where when you see a clean metro map or UML diagram, those are planar embeddings. They reduce visual clutter and improve readability compared to overlapping edges. Third is algorithmic speed. Many NP hard problems become computationally tractable when restricted to planar graphs. So identifying planarity early opens doors to efficient algorithm downstream. So let me show planarity with examples. This is the K4, every pair of 4 vertices connected. Though this drawing shows crossings, we can redraw it without any. The key insight is that planarity is a property of the graph itself, not a single drawing. So we can redraw K4 by moving one edge outside the square and eliminate all crossings. The K5, the complete graph of on 5 vertices. So it's drawn as a pentagon with a 5-pointed star inside. K5 is fundamentally different. No matter how you rearrange the vertices or edges, you cannot eliminate all crossings. So this is the smallest complete graph that's non-planar, a critical threshold in a graph's theory. Next is the K3 and 3. It's a bipartite graph, 2 sets of 3 vertices, fully connected between sets. So you might know this as a utility puzzle. Can you connect 3 houses to 3 utilities like gas, water, electricity without crossing lines? The answer is no. K3 and 3 is non-planar. So why pair K5 and K3-3? Kuratowski theorem gives us the answer. A graph is non-planar if and only if it contains a subdivision of K5 or K3-3. So these are not just examples, they're just fundamental abstractions to planarity, and finding them proves non-planarity conclusively.
Given that we have talked about the planarity and its relation with non-planar or planar subcomponents, in our solution, the algorithm will cut the graph into different substructures and check if there is non-planarity within them. If yes, then the graph is non-planar. In doing this, we will use the depth first search algorithm. Next slide, please. We will record 2 different types of edges. The first one, tree edge, the second one, backward edge, which marks the highest ancestors a node will have. We traverse through the graph in the depth first level, and the farthest children will be marked with the highest distance, or if there is a predecessor that form a circle from a backward edge, it is marked as a circle. And then next slide, please. When a circle is found, we will consider it a piece, and then we will remove the piece. Then the remaining pieces outside the circle will be presented in the forms of intervals, which marks when the pieces start in the whole graph and when it ends. So if 2 pieces are interleaving, then there is a non-planarity within the subcomponent. If the 2 intervals are nested, then it is planar. We are not comparing the pieces naively because we want to ensure a linear runtime. The next slide, please.
Yeah, next is time complexity. Theoretically, the time complexity of the Hopcroft-Tarjan algorithm is order of V plus E. For a planar graph, Euler formula states that the number of edges does not exceed 3b minus 6. Therefore, E become proportional to V, and the entire algorithm run in linear time. Next slide, please. Next is in experimental result and conclusion. First, we tested whether the algorithm can accurately determine the planarity of the graph. Our goal was to verify whether the algorithm distinguishes between planar and non-planar graph. As shown in the bottom right part of the slide, the algorithm worked as expected and produced correct result. Next slide, please. Next, we also measured how the time complexity behaves in practice. We tested the graph with a vertex count range from 100 up to 1,100. The number of edges was set close to the planar limit to ensure rigorous test. As shown in the right graph, there was small fluctuation due to maybe system load, but overall, the execution time trend is very close to big O n. Next, please. Yes, that is our reference list. And yeah, this is the end of our presentation. Thank you.